Today we're going to talk about stress. In statics we learned about how to calculate the equilibrium of structures that are experiencing external forces. And in statics we made one assumption, and that was that all of these structures were rigid. They didn't deform at all, change shape, get larger, get smaller, due to those external forces. But as it turns out, all real materials will deform under external loading. A brick building will start to compress. The bricks itself will compress under the weight of the bricks above it. Tall buildings such as skyscrapers will bend and sway in the wind. And these are examples of deformations due to the external loading. And so before we can talk about the deformations that occur within structures due to external loading, we need to understand what's happening inside the structure that's causing these deformations. This is described as stress. So a natural question is, what is stress? Simply put, stress is a measure of the external forces that are acting over a cross-sectional area of material. So this is better understood by an illustration. So think of a cylindrical rod. So we can apply an external force along the long axis of this rod. So we apply a force P, and you notice that we've applied an equal and opposite force on both ends of the rod because this structure is in static equilibrium. So this force P is acting perpendicular to some cross-sectional area. Because this is a cylindrical rod, that cross-sectional area is circular and is given by pi r squared. So in this case, we have a stress that's acting perpendicular to the cross-sectional area of the rod. Another word for that is it's acting normal to that cross-sectional area. And so this is what's described as a normal stress. Normal stresses are typically denoted with the Greek symbol sigma. So as opposed to a force that's acting perpendicular to that cross-section, you could also imagine a force acting parallel to that cross-section. So let's redraw this circular rod. With the same cross-sectional area. And now instead of an external force P acting along the long axis of the rod, we can imagine a force V acting parallel to that cross-sectional area. And of course we need an equal and opposite force acting at the bottom of the rod. Same cross-sectional area. This force is acting in parallel to that cross-sectional area and is described as a shear stress. A shear stress is typically denoted with the Greek symbol tau. So these are the two fundamental stresses that we're going to encounter throughout this course. Naturally, you could imagine, well, what happens if we have a stress acting at some angle away from perpendicular or parallel to that cross-sectional area? Well, in that case, just like you've done in introductory physics courses, what you'll do is break up that stress, so something that looks like this force F acting at some angle theta. We can break this force F into its components so we can get a normal stress from it and a shear stress from it. So in general, all these external loadings can be described by one or both of normal stresses and shear stresses. So what are the units on stress? Well, we know that we have force and we have area. We know the units of force are typically newtons, and the units of area are, of course, a length squared. And so stress is given by the units newtons per meter squared. This unit is defined as a Pascal and denoted with the symbol capital P and lowercase a. In US units, it's customary to see pounds per square inch. Now the Pascal is an inconveniently small value of stress. And so what that means is you'll often encounter stresses on the order of 10 to the 3 Pascal, 1,000, 1,000,000 pascals. And so it's important to be familiar with 10 to the 3 pascals being a kilopascal, denoted with kPa. 10 to the 6 Pascal, denoted with a megapascal. And 10 to the 9 Pascal, denoted with a gigapascal. So there's one important assumption that we made here in describing these stresses that we'll come back to and revisit later throughout the course. And that assumption is, we've assumed that this force is being evenly distributed across this entire cross-section here. And so what we're actually describing with sigma and tau are average stresses. And as I said, we'll come back to understanding when this assumption breaks down. So now we know what a stress is, and why is it important to engineers? Most materials that we design structures with have some sort of failure point that can be characterized by a stress. And so what you might see is that a material will fail when the applied stress is greater than some ultimate stress. And this value here depends completely on the material you're using. It's going to be different if it's steel, aluminum, or rubber, and so on. And so it's important for us to keep in mind that the external loading generates a stress within the material, and we need to compare what that stress is to the failure stress of the material. Will the load that we're applying cause the structure to break? And so one of the metrics we use in order to design structures in a safe manner is what's known as a factor of safety. And this factor of safety is a measure of the failure stress of the material to the applied stress of the material. It's denoted with the symbol Fs. And it's a ratio of the ultimate stress, which is a material property, to the allowable or applied stress, which is a property that's dictated by what is the load you're applying and what is the shape of the structure you're applying it to. And so in order to design something safely, we have two options. We can vary the loading or the geometry of the structure, or we can vary the material. Both of these will change this ratio here. Typical factors of safety in designing engineering structures are roughly a factor of 3. This can go down to values that are barely above 1, which is sometimes commonly seen in the aerospace industry, and it can go up to values as high as 10 or 11, depending on the safety required for the designing the external structure. This is an important criteria because in class we often are given an external force or are given a shape. In reality, we can only sometimes assume what that force will be. If we design a bridge, we can estimate how many cars will be driving over it at a given time. But we need to be prepared so that that bridge doesn't fall down if one too many cars gets on it, an unexpected number, if something externally is applied that causes the entire structure to fail. So we want to make sure that if we don't exactly know what P will be, if something could ever change, then we design our structures with a factor of safety to account for the unknown. And so in today's lecture, we've introduced you to stress, which is an external force acting over a cross-sectional area. We've described the two main stresses you'll observe, normal stress and shear stress. Normal stress is when the force acts perpendicular to the cross-section, and shear stress is when the force acts parallel to the cross-section. We've denoted what the units of stress are. And we've described how these values of stress that we're calculating can be used to design structures by comparing the stresses we expect the structure to feel to the stresses that are allowable within the particular material that you're using.